Take a look at number 111y, and it's to find the limit of the sequence that's given by this general term. And so, I mean, if you wanted to play around, see what happens when, n is 1, you'll get 1 plus 1, which is 2 to the first power, right? So for instance, a sub 1 is 2, and then a sub 2, when you plug in 2, you get 1 plus a half to the second power, so 1.5 squared. And you can compute that. And then if I do 3, I'll get 1 plus 1/3, which is 4/3 cubed. And so on. I mean, we can take a look at that. The question is, though, as n gets bigger and bigger, are these values 2, et cetera, approaching a fixed value? Are the values of the terms of this sequence, are they getting closer and closer to some fixed value? In other words, does the limit as n goes to infinity exist for this expression? Well, when we go there and take a look at that, I'm going to let y, and you'll see why in a minute, equal the value of this limit, if indeed it exists. And so I'm taking the limit as n goes to infinity of a sub n. And notice what's happening is n goes to infinity, clearly 1 over n, that's approaching 0, right? And 1 plus something approaching a 0 is approaching 1. So the base is approaching 1, whereas clearly the exponent, n, is going to infinity. We get a form 1 to the infinity power, and that's indeterminate form. So what's happening is the base is getting closer and closer to 1, right, as n gets bigger and bigger, right? But what is 1 to any power? 1 raised to any power is 1. So the base is trying to make this go to 1. However, the base is never actually equal to 1, is it? It's close to 1, right? 1 plus 1 over n. So 1 over n is, as n gets bigger and bigger, is never 0, but it's approaching 0, but it's still, right? When n is 1,000, you'd have 1 plus 1,000, right? 1.0001, right? So you're going to get a number that is always a little bit bigger than 1. So anything bigger than 1 raised to a power n, where n is getting bigger and bigger and bigger, right? What's happening to that? Anything bigger than 1 raised to a bigger and bigger power is just going to get bigger and bigger. It's approaching infinity. So you see, we have a battle. That's why it's indeterminate. This limit could be 1, it could be infinity, or it could be something in between. We don't know. We don't have enough information. That's why we call this indeterminate. Now, when you hit indeterminate forms, we have some techniques and tricks. One is, of course, L'Hopital's rule. And you should have seen problems like this in Calc 1 with L'Hopital's rule. They were maybe some of the more challenging ones. But one thing about L'Hopital's rule is, remember, L'Hopital's rule only works on forms that are 0 over 0 or infinity over infinity. And that is not what we have. I can't apply L'Hopital's rule yet. So how can I get a form like this to be, a ratio, right, where we could even possibly get one of these two forms? Well, we're going to make use of a property of logarithms to do that. And so I'm actually going to, as my hint in the problem says, I'm going to take the log of y, so the log of this limit. Now I can push the log inside the limit, because the limit as n goes to infinity, right, n is clearly positive, and the natural log is continuous on its domain, which is everything greater than 0. And so for continuous functions, we can, of course, push that through the limit, right? Because that's how we evaluate continuous functions, by directly, evaluating the limit, right? Plugging in directly. Of course, we're going to infinity here, so we're not plugging it in, but what's the behavior of a sub n? Well, if I take the natural log of that, it's going to be the same thing as the limit as n goes to infinity of the natural log of a sub n. Okay, so that's the hint. So where do we go from there? Well, I'm going to replace a sub n with the expression for the general term here. And I'm going to make use of this property. The natural log of a base raised to a power is what? A multiple of that logarithm. This is an important property of logarithms. You should have remembered those in Calc 1. You did like logarithmic differentiation, where you made use of these various properties. There's 3 different ones that we make use of, and this clearly is the case, right? And so using this property of logarithms, my a here is the 1 plus 1 over n, right, to the n power. So I'm going to bring that power n down, right? So the log of an exponential expression is a multiple of the logarithm of the base of that expression. Okay, so this is, again, something that we have from pre-calculus that we make use of. Properties of logarithms come into play a lot of times in calculus. Okay, what do we have now? As n goes to infinity, clearly n is going to infinity. Put a dot there for multiplication. What's happening here? Well, remember, as n goes to infinity, 1 over n is going to 0. So it's approaching 1 inside here. So it's approaching the natural log of 1. And what is the natural log of 1? It is indeed 0, right? If we were to graph the natural log function, we know that at 1, the value of the natural log function is 0. Right, and the natural log function has a vertical asymptote at x equals 0, but it looks like this. Right. So we know that this thing is approaching the form infinity times 0. Well, that again is indeterminate, right? N is going to infinity, right? Right. So it's trying to make the product of these two values, these two functions, as n gets bigger and bigger, go to infinity, bigger and bigger. Remember, I got 0 here. That we're never equal to 0, right? The natural log of 1 plus 1 over n is never equal to 0. It gets close to 0, right? So it's trying to make the product 0, isn't it? Or very close to 0, something small, right? So you've got a battle going on. One function's trying to make it go to infinity, the other's trying to make it go to 0. It could be something in between. It is, again, indeterminate here, but it's not L'Hopital rule form yet, right? Again, indeterminate forms, 0 over 0 or infinity over infinity. So we've got a second indeterminate form. Do you remember how to deal with this from Calc 1? Well, it's pretty easy. If we have a function, and I'll look at this function n, it's clearly going to infinity, right? Its reciprocal is going to what? 0, right? If n is going to infinity, 1 over n is going to 0, because the form 1 divided by infinity is going to 0. And so I'm going to simply rewrite this product as what? Instead of multiplying by n, I'm going to what? Divide by the reciprocal, 1 over n. That's the same thing, right? Dividing by 1 over n is the same as multiplying by n. You know, think about if n is 2, for instance, dividing by 1/2 is the same as multiplying by 2, and so on. So I haven't done anything other than rewrite this expression, but now you see the top, again, as we said before, is going to 0, and 1 over n now, since n is going to infinity, 1 over n is going to 0. And guess what? Now this form is approaching 0 over 0, which is indeterminate, right? Both of these functions are approaching 0. We don't know what that overall ratio is approaching yet, but now we can use L'Hopital's rule. If you remember, any limit of the form 0 over 0, infinity over infinity, with some restrictions, we can do what? Take the derivative of the top function, or the numerator function, derivative of the bottom function, right? Take the limit of that ratio. If that limit exists, then that limit will be the same as this limit here. So I'm going to use L'Hopital's rule. When I do that, I like to put a little L over the equal sign, and you should do that if you're using L'Hopital rule, indicate where you use it. So I take the derivative of the top. That's a little tricky. It's the natural log of the quantity 1 plus 1 over n. So there's a composition, and so we have to use the chain rule, right? We've got a chain rule going on here. And so when I take the derivative with respect to x of the natural log, and I'm just going to say u here, so I'm going to let u be the 1 plus 1 over n. Then what is it by the chain rule? It's the outer function is the natural log. Natural log is the outer function. U is the inner function. So we take the derivative of the outer function. What's the derivative of natural log of u? That's 1 over u times what? The derivative of the inner function u, which is, we'll just write it as u prime. Okay, so it's u prime over u, right? That's the derivative of natural log of u. So u prime over u. Well, so what is u prime? What is the derivative of 1 plus 1 over n? Well, the derivative of 1 is 0, right? The derivative of 1, now we're taking the derivative, right, of a constant is 0. What's the derivative of 1 over n? Well, I did that over here to remind you. I can write 1 over n as n to the negative 1 power. So simply using the power rule, I'll bring a negative 1 down, subtract 1, right? negative n to the -2, which is -1/n². And so I get u prime -1/n², and 1/u, right? Remember, u was this whole thing, 1 plus 1/n. So 1/u times the derivative of u. Okay, what's the derivative of 1/n in the bottom, right? So the L'Hopital's rule says take the derivative of the top over the derivative of the bottom. Well, 1/n, we just did that, is -1 divided by n². And you can see what happens, right? Notice what happens now very nicely. These two factors are equal, right, for all values of n greater than 0. And so I can basically, divide numerator and denominator by -1 divided by n², or multiply top and bottom, I guess, by -n². And then I'm left with just this, right? That's all. This is the only thing I'm left with, right? This is 1. And now, can I determine this limit? Is this something I can determine? As n goes to infinity, what's happened to this 1/n term? That's going to 0. So this is approaching up top 1, on the bottom 1 plus 0, 1. Is that indeterminate? No, it's 1, right? It's getting closer and closer to 1. Since this limit is getting closer and closer to 1, this limit is getting closer and closer to 1. And of course, this limit is getting closer and closer to 1. And so is this limit, and this limit, and this limit, and this limit, right? But more importantly, right here, notice what we have. The limit as n goes to infinity of the natural log of a sub n is 1, or I'm saying the natural log of y, right, is equal to 1. So is the limit of our sequence equal to 1? No, our sequence limit is y, right? Y is the limit as n goes to infinity of a sub n. What we have is the natural log of y equaling 1. So what is the value of y? Well, you know how to solve this equation, I hope. Y is equal, writing this in exponential form, what's the base of the natural log function? It's e, right? So the logarithm is the power, right? The power being 1 on the base e needed to get y, right? So y is e to the first power, which of course is just e. And therefore, what do we have? Y is e. And so the limit as n goes to infinity of a sub n, in this case, is e. In fact, this is a definition of e, the limit as n goes to infinity of 1 plus 1/n quantity to the nth power, right? This is equal to e. This is even sometimes used as a definition for the number e, which is about 2.71828. Okay, so this was a challenging one because of the multiple things that we had to use. Obviously, understanding the importance of the logarithm and the property of logarithm that allows us to bring this power down. And then we have rewriting this indeterminate form into a form that we can use L'Hopital's rule. And then, of course, applying L'Hopital's rule. And then going back and realizing what we have is not the limit of the sequence, but the natural log of that limit, which we can then solve for the actual value. Okay, so I hope this one helps on this one. This one, again, is the last one in that number 111. So it is rather challenging. Hopefully this helps with this.